What are some of the potential ways or future ways to go about optimizing ketamine?
Let's start with the end, if you will, which is, what do we really want in treatment? What would be the ideal antidepressant? The ideal antidepressant would be a drug that acted rapidly and lasted forever. Right? We would call that basically cure. And we never use the word cure in psychiatry. And we don't even think of the idea of cure. And that's partly because we don't really understand the brain well enough to really know how to completely undo the changes that we see there. So let's start just with the shortest version of that, which is, what if we could take ketamine, which has a short duration of antidepressant effectiveness at the beginning, somewhere between, say, 3 and 7 days, and make it last 2 weeks or a little bit longer. And you might say, well, why would you think that that would be a reasonable thing to try to do? It's because when you give ketamine to patients in the long run, you can space out the treatments more and more. In other words, you start with giving it twice a week, then you go to once a week, then you go to every other week, and then eventually many people will get to every 3 weeks or maybe even every 4 weeks. So it suggests that there are some mechanisms that are triggered when we give ketamine, or existing as a precondition for treatment-resistant depression, that shorten the duration of the effectiveness of ketamine. And so we've been interested in that question for a long time. And we did a study that really spurred our interest in this question. And it was led at our site by my colleague, Chadi Abdullah. And what we did was to try to block a certain molecular switch that gets triggered when you give ketamine. Downstream, one of the proteins that gets activated inside nerve cells that triggers the regrowth of those synaptic connections. That protein's called mTOR, and the drug we use to manipulate it is called Rapamycin. It's a blocker of mTOR. Now, you'll recall from the animal studies that mTOR activation was implicated in the antidepressant effects of ketamine. And so we did a study to try to show that that was somehow involved in humans. We gave the highest dose of rapamycin, the mTOR blocker, that we felt would be perfectly well tolerated by everybody in the study. Rapamycin is an immunosuppressing drug, and that was in our mind as well, for a reason that I'm going to come back to in a little bit. So we gave rapamycin with ketamine. So in the same group of 20 patients with treatment-resistant depression, they completed one ketamine day where they got just ketamine, plus placebo, of course, and then the other day they got ketamine plus rapamycin. And the remarkable thing was that the response rate at 2 weeks, when they got just ketamine, was about 13%. And when they got the same people, the same depression, if they had gotten pre-treated with rapamycin, their response rate was over 40%.
I'm no scientist, but that seems non-trivial.
It seemed to us to be non-trivial. It was also a little bit perplexing in the sense that we knew we were giving a drug that had the potential to block mTOR in the brain. And if mTOR activation was critical, then why didn't rapamycin block the antidepressant effects of ketamine? And one of the ideas that we are wrestling with is maybe the immunosuppressive effects of rapamycin, which is it's a powerful immunosuppressant, are related to its ability to extend the antidepressant effects of ketamine. And in particular, you may recall that I said that the antidepressant effects of ketamine, at least in animals, seem to last about as long as the newly created synapses. And so we assume that as those synapses are being gobbled up, that the antidepressant effects are going away. So what is doing the gobbling up? It turns out that one of the critical mechanisms that gets engaged are the primary immune cells in the brain. And these, Tim, I think are maybe your new favorite cells, the microglia.
I'm fascinated by microglia. I just like saying it too. But yes, microglia. Please continue.
Yeah. So microglia are really interesting because they have different modes of function. In certain circumstances, they can promote nerve growth in the brain. In another circumstance, when synapses get immunologically tagged, they can surround them and literally eat them up. In fact, over development, there are certain programmed ways that synapses are eliminated, and microglia are involved in that. But when you have inflammation in the brain, as you do in depression, microglia are involved, and we think they contribute to the initial deficits in synaptic density in depression.
Are microglia correlated, or is there a causal relationship between our subjective experience of stress and microglia activity?
Yes. So microglia tend to be activated under conditions of severe and persisting stress like you have in depression. The paradox, and I don't want to get us too distracted because frankly I don't understand what we found. So I can't really explain it. But in patients with post-traumatic stress disorder, we find both in patients while they're alive with PET scanning and in analyzing postmortem brain tissue that the microglia are suppressed. And I've been talking to colleagues about this, and they think, well, maybe at one point they were activated, but maybe there's kind of in a burned out state, an exhausted state.
Microglia are tired. They're on the bench, out of the game.
Exactly. Something like that. I don't really know, and I don't think anybody does what's going on with the microglia. But it's really interesting to me that you have these two stress-related disorders, one like major depression, where you get a lot of cortisol in the body and the microglia tend to be activated in the brain. And then you get the opposite pattern in PTSD where you don't tend to get so much cortisol chronically, and you don't tend to get so much microglia activation chronically. So we've stumbled onto something that we think is important that's different in these disorders that we don't yet quite understand. But for the antidepressant effects of ketamine, what we think is happening is that we might be preventing the microglia from gobbling up the newly created synapses. And so instead of lasting a couple of days, we get like a full course of treatment. How long does rapamycin extend the antidepressant effects of ketamine? We don't know the answer to that because since we didn't expect to see it, we only designed the study with a 2-week window of follow-up. So we'll have to do, longer studies to figure that out. But we're really interested in developing this idea, both from the point of view of academic research, and I have a colleague that I've collaborated with for many years, Tom Su in Taipei, who is doing a study looking at this combination. And then we're developing a version of this idea, one that we think may be optimized for use in the treatment environment within a company called Freedom Biosciences that I'm associated with.
Touching again on the rapamycin plus ketamine, certainly people can go on PubMed and search mTOR and ketamine, and there's a lot to read. If you haven't published this, then of course no need to get into it, or if you don't want to disclose it, that's fine too. But what was the dosage range that you decided upon, or maybe the precise dosage or protocol for the rapamycin that you determined or hypothesized would be well tolerated?
Gosh, I think it's 6 milligrams.
6 milligrams.
Oral rapamycin. And we may have stumbled onto something by giving that dose. And what I mean by that is that we thought it should get into the brain at 6 milligrams. And we were pretty confident that it would get in the brain and would have some effect in the brain. But rapamycin turns out to be actively pumped out of the brain. And so the concentration that we achieved was probably kept quite low by this active clearance mechanism. And so what we think we did was to stumble on a combination that was in a kind of a sweet spot, high enough to interfere with the gobbling up of the synapses, but not so high to interfere with the antidepressant effects. So a little bit of serendipity.